welcome to today's deep dive. If you're joining us right now, it means you're likely staring down the barrel of the VMware 5V0-44.21 exam.
Yeah, or maybe you're just operating as an architect in the telecommunications space and, you want to validate your knowledge of how massive software-defined telecom networks actually run.
Right, exactly. Either way, we are thrilled you're here. Today, our mission is strictly focused. We are decoding the 5V0-44.21 exam.
Which is a beast of a test.
It totally is. We've pulled a stack of official practice questions and architectural documentation, and we're going to dissect the questions, the correct answers, and critically, why the distractors are wrong. So, okay, let's unpack this, starting with the metadata of what you're actually up against when you sit for the test.
Yeah, it's crucial to understand the parameters before you step into that testing environment. You really need to pace yourself appropriately.
Precisely. So looking at the exam outline from our sources, here are the exact stakes. You are given 105 minutes to navigate 55 questions.
Wow.
Yeah, it's tight. The format is a mix of single choice and multiple choice. The entire exam is delivered in English, and you need a scaled score of 300 to pass.
Which basically means you do not have time to second-guess the core architectural concepts.
No, you got to know it cold.
Right. And I want to pause right here and talk directly to you, the listener, about why passing this exam is actually significant. This isn't just an exercise in memorizing flashcards or regurgitating acronyms.
Definitely not.
The 5V0-44.21 validates that you fundamentally understand how to orchestrate highly complex, globally distributed telco cloud environments. I mean, the industry is deep into the transition toward cloud-native network functions and complete virtualization.
Yeah, the old physical hardware days are gone.
Exactly. Passing this means you've proven your capability to design, deploy, and maintain the critical infrastructure that underpins modern 5G and edge communication networks.
That sets the stage perfectly. So let's get right into the architecture. A major theme on the exam is understanding the boundaries between local and global management. There is a scenario here, question 1 in our stack, that tests your knowledge of local infrastructure resources.
Oh, this is a classic one.
Yeah. The question asks you to identify the specific component in the VMware Telco Cloud Automation architecture that's responsible for managing resources at a specific data center site.
At a specific site. Key phrase there.
Right. The options provided are the TCA control plane, the TCA manager, VMware Cloud Director, and Tanzu Kubernetes Grid. The correct answer, option A, the Telco Cloud Automation Control Plane.
What's fascinating here is the really rigid hierarchy VMware enforces in this architecture. The control plane is strictly your local execution environment.
It doesn't look outside its own bubble.
Exactly. It interfaces directly with the local virtual infrastructure manager, the VIM, whether that happens to be vCenter Server or an instance of VMware Cloud Director. It manages the compute, the storage, and networking resources localized to that specific physical site.
Right. And it's important to understand why the distractors are incorrect here. VMware Cloud Director and Tanzu Kubernetes Grid, they're infrastructure layers.
Yeah, they're the foundation.
Right. They provide the platform for virtual machines and containers, respectively. They are not the telecom orchestration plane itself. They execute the commands. But the TCA control plane is what actually manages those resources from an automation perspective at the site level.
Exactly. The control plane sits right above those infrastructure layers. It makes sure that the lifecycle operations of your network functions execute flawlessly on the local ESXi hosts or Kubernetes clusters, but it doesn't have the global view.
Which brings up the next logical layer of the architecture, flowing seamlessly into question 2.
Right, the macro level.
Yeah. Now we're shifting from local execution to global control. Right. So the exam asks, what is the primary responsibility of the VMware TCA manager in a multi-site deployment? And you're given distractors like managing local cooling systems, directing physical power supplies.
Or handling mobile subscriber billing.
Yeah. Obviously, those are completely outside the scope of Telco Cloud Automation. The correct answer, option B, is that the TCA manager provides a centralized interface for global service orchestration.
Those distractors are a bit obvious, but they test your understanding of where TCA actually sits in the OSI model and the management stack. It isn't an orchestrator, it's not a facilities management tool, and it's not a BSS or OSS billing system.
Right.
The TCA manager is your single pane of glass. Think about it. When you have 50 or 100 edge sites, each running their own local TCA control plane, you cannot have administrators logging into individual sites to deploy a new 5G core component.
You would have configuration drift immediately.
Without a doubt, it'd be a nightmare.
So, to create a memorable analogy for you, if the control plane is the local factory floor manager, ensuring the actual machines are running at one specific plant.
Then the TCA manager is the global CEO.
Yeah.
The CEO is looking at a map, designing, onboarding, and deploying services across multiple locations from a single interface. The manager acts as the global brain, while the control planes act as the local nervous system.
That is a critical distinction for the exam. Global brain versus local nervous system. Now, for the global brain and the local nervous systems to interoperate with network functions from, say, Ericsson or Nokia or Mavenir, they must adhere to strict industry standards.
Oh, the alphabet soup.
Yep, the alphabet soup. That brings us to Section 2 of our deep dives, Standards and Orchestration. Question 3. Tests your knowledge of the ETSI MANO framework.
Classic.
It specifically asks which specification defines the standardized interface between the NFV orchestrator and the VNF manager. You're presented with SOL-001, SOL-002, SOL-003, and SOL-005. The correct answer you need to select is option B, SOL-003.
The ETSI NFV standards are heavily tested, so you really need to know these interfaces cold. To break this down, the NFV orchestrator, or NFVO, handles the lifecycle of the overall network service.
The big picture.
Right. While the VNF manager, or VNFM, handles the lifecycle of the specific virtual network function, SOL-003 is the API specification that dictates exactly how the NFVO talks to the VNFM.
And to add to that, understanding why the other SOL standards are wrong is honestly just as important. For example, SOL-005 defines the interface between the OSS and BSS layer and the NFVO, which is often referred to as the OS-MOD-NFO reference point.
Yeah, that's higher up the stack.
Right. And SOL-003, between the orchestrator and the manager, you end up requiring custom plugins for every single vendor's network function.
Which completely defeats the entire purpose of network functions virtualization. Standardization at the SOL-003 level ensures that a VMware orchestrator can seamlessly instantiate, scale, or terminate a third-party VNF because they're both speaking the exact same API language for lifecycle management operations.
They're speaking the same language. Moving down the stack into the containerized world, question 4 focuses on Kubernetes architecture within the telco environment. The question asks you to identify the primary function of a management cluster compared to a workload cluster.
Okay, shifting gears to K8s.
Yeah. The options suggest things like hosting production application traffic, providing localized storage, or serving as a backup repository. But the correct answer, option C, is that the management cluster manages the lifecycle of multiple workload clusters.
If we connect this to the bigger picture, this is the classic separation of control plane and data plane applied directly to Kubernetes infrastructure. In a VMware Tanzu environment, the management cluster utilizes Cluster API to deploy and manage other clusters.
So it's essentially a cluster that builds clusters.
Precisely. It pushes out the Kubernetes versions, manages the node pools, and handles the scaling of the infrastructure itself. The distractors in this question, like hosting production traffic, describe the workload cluster. You never want your user plane function routing gigabytes of mobile data on the exact same cluster that's trying to manage infrastructure state.
Right, because they'd be competing for resources.
Exactly. If a massive spike in user traffic overwhelms the workload nodes, your management cluster must remain isolated and responsive so it can actually provision additional nodes to handle that load.
Here's where it gets really interesting, especially from a network architecture perspective. Section 3 is all about advanced telecom networking.
My favorite topic.
Oh yeah. Question 5 is highly specific to Kubernetes networking in a telco context. The question asks, which Kubernetes networking component allows a single pod to have multiple network interfaces for separating management and data traffic?
Multiple interfaces.
Yes. The options are the Multis plugin, Entrea plugin, Calico plugin, and Flannel plugin. The answer is option A, the Multis CNI plugin.
This is a scenario where you really have to understand the limitations of standard Kubernetes. Out of the box, a standard CNI like Entrea or Calico, which are both excellent primary CNIs, by the way, they typically assign a single ETH interface to a pod.
Which is fine for a basic web server.
Right, for a web server, that's perfectly fine. But for a telco workload, it's an architectural non-starter.
Because in telco, you are dealing with strict physical and logical separation of your control plane, user plane, and management plane networks. If you pump hundreds of gigabits of user video streaming data through the exact same interface you rely on for SSH or API management access,
You're going to drop management packet.
you're going to lose access to the box entirely.
Exactly. And that's where Multis comes in. Multis acts as a meta plugin. It doesn't replace Entree or Calico. It actually sits above them. It allows you to invoke your primary CNI for that standard Ethernet management interface, but then it allows you to attach secondary, highly specialized interfaces directly into the pod.
So you can keep the traffic separate.
Yes, you can attach a MacVLAN or an SRIOV interface directly to the container, specifically for that high-throughput data plane traffic, ensuring complete isolation.
And speaking of those high-throughput interfaces, question 6 directly addresses SRIOV.
A huge topic on the exam.
Massive. The question asks why single-root input-output virtualization is typically implemented in a telco cloud environment. The distractors claim it reduces physical space, shares virtual disks, or simplifies user accounts. The correct answer, option C, is that it provides network functions with direct and fast access to hardware.
To really understand the necessity of SRIOV, you have to look at the overhead introduced by standard virtualization. Normally, a virtual machine uses a virtual switch, like a vSphere distributed switch, to communicate with the physical network card.
Meaning the hypervisor has to process every single packet.
Every single one, which introduces CPU overhead and, more importantly for telco workloads, latency and jitter.
Yeah, when you're processing 5G core traffic, adding a few milliseconds of jitter per hop is completely unacceptable.
Right. So SRIOV takes a physical PCIe device, like a high-speed network card, and presents it as multiple separate virtual functions. The VM or the pod binds directly to that virtual function, completely bypassing the hypervisor's virtual switch.
Bypassing it entirely.
Entirely. You get bare metal network performance and incredibly low latency while still maintaining the automated deployment benefits of a virtualized environment.
It's essentially an express lane straight to the silicon. Okay, moving on to section 4, automation and deployment at scale. Once we have the networking configured, we have to provision the actual host infrastructure. Question 7 asks about the primary purpose of using a host profile during the zero-touch provisioning of edge server nodes.
VTP?
Yep. The distractors mention monitoring physical temperatures or assigning local operator permissions. The correct answer, option D, is to automate the hardware and operating system configuration.
Zero-touch provisioning, or ZTP, is mandatory for edge computing. If a telco provider is rolling out thousands of cell site routing nodes, sending a highly paid VMware engineer to manually configure ESXi on every single physical server is economically impossible.
Not to mention the configuration drift. Somebody will inevitably configure the wrong MTU size on a vSwitch, or they'll forget to point the host to the correct NTP server.
Exactly. It's human error. But a host profile in vCenter captures the known good golden configuration of a reference host. It captures the vSwitch topologies, the storage routing, the syslog server settings, the kernel parameters, everything.
So it's perfectly consistent.
Perfectly. When a new bare metal server boots up via PXE in the remote edge location, ZTP automatically applies that exact host profile. It guarantees that the operating system configuration is completely standardized across thousands of hosts without any human intervention.
Magic of zero touch. Once those hosts are automatically provisioned, we actually deploy our services onto them. Question 8 asks what a virtual deployment unit, or VDU, specifically represents within a cloud service archive package.
The CSR package.
Yes. The distractors suggest it's a geographical region or physical network cables. The correct answer is option B, that a VDU represents the smallest functional unit, such as a specific virtual machine or container.
To contextualize this for you, a Cloud Service Archive, or CSR, is the standardized package format defined by TOSCA. Inside that package, you have your network service defined. A complex virtual network function, like an IP multimedia subsystem, for example, is rarely just one single VM. It might be composed of a database tier, a signaling tier, and an application tier.
It's a collection of building blocks.
Right. And each of those individual building blocks mapping to a specific VM or container instance is your VDU.
So multiple VDUs stacked together to form the complete network service.
Yes. The VDU defines the compute, the memory, and the storage requirements for that specific node. The overarching VNF is simply a collection of these VDUs networked together.
Which leads perfectly into question 9, focusing on the deployment of those packages. The question asks, what is a mandatory requirement before a network service can be successfully instantiated in the TCA environment? Distractors include manually rebooting hardware or powering off virtual machines. The answer is option B, the service descriptor and packages must be successfully onboarded.
Before the orchestrator can allocate CPU cycles, assign IP addresses, or deploy VDU, it needs the architectural blueprint. That blueprint is the network service descriptor and the VNF descriptors.
It essentially tells the TCA manager, I need 3 database VDUs, 2 application VDUs, and here is exactly how the virtual networks must connect them.
Precisely. Onboarding is the process of uploading those TOSCA templates and CRSR packages into the TCA catalog. Until that onboarding is successful and the system actually validates the syntax of the descriptors, the orchestration engine has 0 instructions to execute. You cannot instantiate what the system does not yet comprehend.
No blueprint, no building. All right, we are in the final stretch here with Section 5, keeping it alive. We've automated our edge hosts, bypassed the hypervisor for speed, and onboarded our descriptors. Now, how do we survive a hardware failure?
The most important part.
Yeah. Question 10 asks, what is the benefit of applying an anti-affinity rule when deploying redundant instances of a critical network function? The distractor suggests it forces instances onto the same server for low latency or restricts traffic to a single virtual switch. The correct answer, option C, is that it prevents multiple instances from running on the same physical hardware host.
So what does this all mean in an enterprise architecture? Well, in vSphere, you use Distributed Resource Scheduler, or DRS, rules to govern workload placement. If you have a highly available database cluster with 3 nodes, and DRS happens to place all 3 of those VMs on ESXi-host-01 just to balance cluster memory.
And then ESXi-host-01 suffers a catastrophic motherboard failure.
You just lost your entire database cluster simultaneously.
Yeah, that's bad.
It's the ultimate don't put all your eggs in one basket scenario. Your software-level redundancy was completely undermined by hardware-level consolidation. An anti-affinity rule explicitly forbids DRS from placing those specific VMs on the same physical host. If you have 3 redundant instances, the system forces them onto 3 separate physical servers.
So if one physical host loses power, the service just survives because the redundant instances are safely running on completely different hardware.
Exactly. You only lose 1 instance of the service, and the remaining instances simply absorb the traffic.
And it's critical to note that in constrained edge environments where you might only have 2 physical hosts, applying strict anti-affinity rules requires careful capacity planning. Because if an upgrade requires spinning up a temporary 3rd instance, a strict rule might actually block the deployment if a 3rd physical host isn't available.
Oh, that is a brilliant point. Architects really have to balance strict availability requirements against the physical compute constraints of remote edge sites.
Thank you for joining us on this deep dive. Keep diving into the documentation, keep testing your architectures, and we'll catch you next time.